Hi all, hope all of you are fine, safe and doing good. So in this lecture, we will discuss about the arithmetic circuits, which is from module 6. We will cover one or two topics in this lecture and we will cover the remaining topics in the following lectures. Okay, so this is the block diagram of a generic digital processor. All of you are familiar with this diagram. And this shows the diagram shows the architecture of a digital processor where we have memory, input, output, control unit, then the data path. So here this data path means it is actually equivalent to the arithmetic and logic unit of a general processor where we normally do the addition, multiplication, etc. Okay, so this is just an architecture of a digital processor. And first topic is adders. We will discuss about the adders. So full adder, hope all of you are familiar with the full adder, half adder, etc. So here we will discuss about the full adder first, and then we will see some examples of full adders. So full adder, as you can see from the diagram, a full adder consists of two inputs plus a carry in. A and B are inputs, and then there is a carry in. The outputs, we can say the sum, and then there is a carry out. Okay, so all together we can consider there are three inputs and two outputs. Fine. So consider we have a truth table here. We will see the inputs A, B and the carry inputs. So consider the first case when input A and B are 0 and the carry input is 0, then the sum will be obviously 0. Okay, and the carry out is also 0. And we will see what does this carry status means. Then coming to the second one, 0 0 and the carry input is 1. So the sum is 1 and the carry is 0. Similarly 1 0, sum is 1, carry 0. 1 1, sum is 0, carry is 1. Then 1 0 0, sum is 1, carry is 0. 1 0 1 is again sum is 0, carry out is 1. 1 1 again same, sum is 0, carry out is 1. And then comes the last one, 1 1 and carry input is 1. So we have the sum which is equal to 1 and the carry output is 1. 1 plus 1 is 1 0 plus 1 1 1, just like that. So this is a common one which is familiar to all. Okay, so now the carry status. So we can see that the carry output is somehow related to the carry input. So we have in the first two cases, whatever comes in the carry input, we will have the 0 at the output side. So we say the carry is deleted. Okay, so 0, whether the carry input is 0 or 1, we have carry output is 0. So it is deleted, just like we are deleting that carry input. Okay, and then the third one and the fourth one, fifth one and the sixth one, we have whatever comes in the carry input which is propagated to the carry output. So when it is 0 in the carry input, we will have the carry output as 0 itself. Similarly, if it is 1 in the carry input, we will have the 1 at the carry output. So we say that it is propagated. Okay, now the last one, seventh one and the eighth one, whatever comes in the carry input, the carry output will be always 1. So we can say it is generating. Okay, generate. So even if it is 0 or 1 at the carry input, we will have 1 at the output, at the carry output. So it is actually generate. Okay, so that is what this carry status means. So the first two one is delete, the last two one is generate, and the other remaining 4 are propagate. Okay, so the first one is binary adder. You are familiar with this equations or functions. The sum is equal to a XOR b XOR ci. When we expand the equations, we have a b bar c I bar plus a bar b c I bar plus a bar b bar ci plus a b c I. Okay, this is I. Okay, and similarly the carry output is equal to AB plus BCI plus ACI, the carry input. Okay, so this is a familiar one. Just like we discussed, we can express the sum and carry as a function of propagate, generate and delete. Okay, so we can define the generate, which is represented as G, as AB, product of both A and B. Then the propagate means A XOR B, and delete means A bar dot B bar, like that. The carry output with respect to the generate and propagate is equal to G plus PCI. Similarly, the sum, we can express sum in terms of generate and propagate, that is S is equal to P XOR CI. And we can also derive the expressions for sum and carry output based on D and P, like that. Okay, and then we will discuss the first example, which is called the ripple carry adder, and it is also called as the static adder. Okay, consider if there are n numbers of bits, then we have to use n full adders. We require n full adder. So this is just an example of 1 2 3 4 4 full adders, and the main drawback of this circuit or carry adder is it has got high propagation delay. Okay, so like that, one full adder output is given to the input of second one. We have inputs A0 B0, A1 B1, A2 B2, A3 B3, like that. Carry input for the first stage, sum, then the carry output of the first stage is given to the carry input of the second stage, and like that we have S0, S1, S2, S3, and finally we have a carry output. So the worst case delay linear with the number of bits, that is, the delay is dependent upon the number of bits. The T delay is equal to O, where it is represented in terms of n, and the T delay of adder is equal to n minus 1 into T carry plus T sum. So our goal is to make the fastest possible carry path circuit. Okay, just like to reduce shows one way to implement the full adder. We can take the logic equations one method is to take the logic equations and convert it directly into the CMOS logic. Okay, so the equations are like, we are all familiar with that. I'm not displaying that equations because while you are taking notes, you should mention that that the equations for sum S is equal to A XOR B XOR CI, that is equal to A B C plus CI into A plus B plus CI. Similarly, for carry output, we know that equations AB plus BC plus AC. We can take that C outside, which is common, so it becomes AB plus C into A plus B, or again we can write it as AB into CI into A XOR B. Okay, so the same is represented in terms of the complementary CMOS logic, where we have N MOSFETs as well as the P MOSFETs. So this represents the carry output, and the carry output CO bar is obtained here. So for the carry output, we have A into B, or A into B plus parallel circuit A plus B into C, like that. Then we take the complementary using PMOS. So this is the CO bar or the carry output bar, and when we give a give an inverter circuit, we will get the carry output. Okay, similarly, to find the sum, we have the circuit where it is A plus B plus CI into CO bar. This one is CO bar. Okay, plus A plus B plus CI, the circuit. Okay, and then comes the complementary of that. And finally, we are using an inverter to get the sum. So we get the sum as well as the carry output here. So this circuit is used to obtain the full adder or to realize the full adder using the complementary CMOS logic. Okay, the one of the drawback, we can say that it consists of 28 transistors. So we can say that the delay will be more as the number of transistors are more. Okay, so we can make use of an inversion property to reduce the number of transistors. The inversion property means when inputs are in true forms, the sum and carry are in complementary form. So if the inputs are in complementary form, the sum and carry are in true form. So we can reduce the delay of inverters using this logic or a method. Okay, so we can minimize the critical path or delay by reducing the inverting stages. What happens is we are removing the inverter stage at the end of each stage with the help of this inversion property. Okay, so this is the topic 1 or lecture 1, and we will discuss the other topics in the following lectures. Okay, thank you.